For much of human history, motion has been something puzzling. In this photo, we see a picture of someone jumping into water. To create a picture like this, many images are photographed at regularly spaced intervals, say every 0.2 of a second. These images are then superposed on top of each other. Clearly, this motion is very complex and difficult to comprehend. A big part of trying to understand any phenomenon is coming up with the right approach.
For centuries, some of the greatest thinkers pondered the question, what keeps things moving?
It is not until the mid-16th century that we begin to see what is still considered an acceptable approach to the issue of motion. But just what is motion? What leads us to believe that something is moving? A good answer is that we know something is moving because its position, and we use the term to mean location, is changing. Given this, then, isn't it reasonable that in order to analyze motion, we must be able to define position? So how do we do that? How do we specify, that is, assign a value to, an object's position? Here we have a small aluminum block. How could we specify its position? In other words, how could we state where it is? You could say that it is so many centimeters from the left and bottom edges of the green area, or so many centimeters from the left and bottom edges of the computer screen. You could even say it is so many centimeters from you in a particular direction. In each case, however, note that in order to specify the position of the object, you must do so with respect to something else. So this is very important. You can only specify the position of something if you do so relative to some other object, that is, relative to some reference. So here we can state that the block is 5 centimeters to the right of the cylinder. In this case, the cylinder is our reference. Of course, we can also state that the cylinder is 5 centimeters to the left of the block. In this case, we would be stating the position of the cylinder and using the block as our reference. So how do we, in a case like this, express the position of this block? We can't simply say it's 5 centimeters away from the cylinder. Note that in the previous cases we were able to say that it's 5 centimeters to the right of the cylinder, but here it's neither to the right nor the left, nor is it above or below. So simply saying that it's 5 centimeters away opens up to the possibility of it being anywhere along a circumference of a circle of radius 5 centimeters whose center is right here. So simply saying that it's 5 centimeters away means that it could be anywhere along this blue line. In a case like this, one proper way to express the position would be to say it's 5 centimeters to the right and 3 centimeters up. Of course, we could also say it's 3 centimeters up and 4 centimeters to the right. Another possibility is to simply say it's 5 centimeters away and at an angle of 36.9 degrees counterclockwise from this line. Of course, that last part is still a bit clumsy because I have to say this line. What we need is a more explicit way of communicating just what line I'm talking about. So perhaps the best way to express the position of something is to use a coordinate system. So throughout this course, whenever we want to express the position of something, we'll do so with respect to an XY coordinate system. So in this case, we can say that the block is 5 centimeters away from the origin and at 36.9 degrees counterclockwise from the positive X direction. Notice that explicitly and accurately states the position of this block. We can also state that the block is at position X equal 4 centimeters, Y equal 3 centimeters. Students in physics courses are asked to solve many problems. Now, problems are solved in stages, and perhaps the most important stage is what is often called the preparation stage. In this stage, the student is expected to create a visual representation of certain aspects of the problem. These visual representations often include the use of an XY coordinate system. Suppose for a moment that you are given a problem involving a moving motorcycle. What we have here is a visual representation of its position at 2 distinct points in time. These are supposed to be stopwatches and indicate that at time equals 0, that is at the exact moment the stopwatch is pressed, the motorcycle is at x equal 25 meters. Note that I have included the units on the axes. 15 seconds later, and we can assume here that the stopwatch has not made one or more complete revolutions, The motorcycle is at x equal 430 meters. Note that in the context of a problem, you would have gotten this information from reading the problem. Modeling the problem in this way, creating this visual representation, frees you from having to constantly refer to the text of the problem as you move into the more analytical stages. Note that our diagram tells us nothing about how the motorcycle was moving in those 15 seconds. We can't tell if it was slowing down, speeding up, or traveling at a constant speed. Now we don't want to have to be drawing stopwatches all the time, so what we normally do is indicate the times as we have done here. Instead of drawing stopwatches, what we have done is we have simply placed T0 and T1. So T0 is the time corresponding with when the motorcycle is at its initial position of 25 meters, and T1 is the time corresponding with the motorcycles being at its second position, which is 430 meters. Sometimes students find this a bit confusing and would prefer to use 1 and 2, and that's okay instead of 0 and 1. Some students prefer to use I and F for initial and final. Initial time, final time. So these are all individual choices that I believe students can make for themselves. I find that students with some kind of background in computer science prefer to start with 0. Again, it's your choice. If you're wondering whether or not you need to be able to draw something like this motorcycle that we have here, the answer is no, you don't need to be able to draw objects like these. In physics, we have something called the particle model. Now, this particle model allows us, under certain circumstances, to represent things as particles, to treat things as particles. So what circumstances could those be? Well, if you're interested only in the position of something, if you're interested only in its mass, its velocity, its acceleration, if you're interested in these things and not in the actual dimensions, how long it is, how tall it is, then you can treat it like a particle. And so we represent particles as points. And you all should know a point is a geometric abstraction that has no dimensions. Obviously, we can't draw something that has no dimensions, so we draw little dots. So these dots then are now used to represent the motorcycle. The nice thing about the particle model is that if you have a problem involving a boat, you can represent the boat using these dots. If you have a problem involving someone running and that person is here and then the person is here, you can represent that person using these dots. So that introduces you to the particle model. Instead of writing down the numbers here, it is preferable that you write symbols. So here we have the initial position x0 and the final position x1. Note you could use 1 and 2 or I and F, initial and final, but you must be consistent. That means if you use 1 and 2 here, you must also use 1 and 2 here, and likewise here, T1, T2, x1, x2. So consistency is very, very important. So here we've placed the symbols and here we place the values. So when you're going to solve a problem, the first stage involves creating a diagram like this. And usually accompanying this diagram, then you'd have your list of values. So essentially what you're doing is you're summarizing the problem. You're trying to get what might seem like a huge problem. You're trying to reduce it into something manageable. So that concludes this little introduction, and so you should be familiar now with the term frame of reference. We're using this XY coordinate system as our frame of reference. So until the next lesson.